Welcome all. So, today we will continue our analysis of the rectangular structures with openings subjected to blast loading. Okay. Last time we have seen the effect of the openings on the frontal face, okay, because as we told earlier in the beginning of the lecture, we are dealing with the most common case where the openings are present only in the front surface. Okay. So, we are trying to analyze the structures having opening on the front surface, and we are trying to categorize the area that is subjected to openings. Okay. And what we are trying to do is that we are trying to get an equivalent area. Okay. So, we will continue with the analysis. Okay. So, in addition to the earlier delta n consideration, there are additional considerations on window failure. Okay. So, window or door breakage requires finite time before pressure relief occurs. Okay. So, it needs some time so that the mechanism is engaged, the resisting mechanism of the windows and door is engaged, it is subjected to the loading, and after that subsequently the failure occurs depending upon the material that is there. Okay. A ductile or a brittle type of failure will occur. Okay. This failure time can be evaluated using resisting functions and the dynamic procedures. Okay. So, the time required for the total failure to take place, okay, that can be easily analyzed using the resistance of the structure, the dynamic resistance of the structure, and the effect of the dynamic load applied to it. Okay. Meaning, what is the dynamic loading on the structure, what type of failure it is going to cause, whether it is going to cause a bending failure, shear failure, or a bearing failure, brittle type of failure, or elastic failure. So, this will depend upon the resistance mechanism as well as the loading mechanism. Okay. So, if we know both of these things, we can analyze how this thing will occur, but nonetheless whatever happens, there some time will be required for this mechanism to engage. Okay. So, this breaking time must be accounted for in determining window contribution to the blast pressure on the wall. Okay. Let us say if this failure is occurring very late, okay, the door and the windows are able to resist the effect of the blast for a significant amount of time, okay, then the distribution of the internal loading, internal pressure will be different from a mechanism where it is going to break instantly. Okay. So, this breaking times also becomes a key feature when evaluating the effect of the blast on a structure having so called opening type of mechanism. If covers are resistant and they do not break quickly, the clearing time should be treated as that of a solid wall. Okay. It will not reduce, okay, because a significant amount of time would have passed, okay, and the blast loading would have been engaged by the entire surface. Okay. So that this becomes an equivalent as a solid wall. Okay. So, the treatment of the clearing time depends upon all of these factors. Okay. So, exterior front walls will with openings. Okay. So, we are trying to calculate the weighted clearing distance and the clearing time. So, weighted clearing distance is nothing but the sum total of the area of the individual subdivisions that we have seen earlier, and this is the net wall area excluding openings. Okay. And it depends upon the delta factor that depends upon the relative location of that area. Okay. So, reduced clearing time is calculated by substituting this in the equation, okay, where Cr is the sound velocity in the reflected region, R is the ratio of S prime to the large wall dimension, height or half width. The resulting front wall load follows same curve as for the solid wall with reduced clearing time. If the clearing time is reduced, then as we have seen earlier, it will follow the same curve as the proper solid wall. Okay. So, continuing ahead. So, the effect on the interior front wall with openings. Okay. So, the average pressure on the interior face of the front wall builds up similarly to the average pressure on the exterior back wall of a closed structure. What does it mean? The average pressure on the interior face of a front wall, okay, if this is the front wall, okay, no opening, and this is the structure with opening. Okay, let us say this is the opening. Okay, so the average pressure on the interior face of the front wall. Okay, this is the interior face of the front wall. Okay, we are looking from this side, builds up similarly to the average pressure on the exterior back wall of a closed surface. So the build of the pressure on this surface, okay, with opening is similar to the build up of the pressure on the back wall, okay, the exterior side of the back wall. Okay, so they are similar in nature. This thing is similar to this surface. Okay, so the vortices will form around the interior edge of all front wall openings. Okay, there will be a formation of the vortices because the opening has sudden change in the geometry. So once there is sudden change in the geometry, the vortices will form across all the interior edges of all the front wall openings. Okay, their load reducing effects are typically neglected in standard calculations. Okay, due to the formation of the vortices, okay, and change in the direction, whatever is the reduction in the pressure, that is normally neglected. Why? Because they are highly uncertain to predict. Okay, and nonetheless there might be a stress concentration at this discontinuity surface. Okay, so it negates the effect of the reduction in the pressure. Okay, so that is why they are typically neglected. Okay, the shock fronts will enter through the openings, travel across the interior faces and subject the walls to the internal pressure. Okay, so the structure is there. Okay, opening is there. Okay, the shock front will enter through this openings, travel across the interior face and subject the wall. Okay, it will subject this wall to the internal pressure. Okay, once it reaches the side walls, okay, once it reaches the sides wall, subsequently the blast is reflected back to the interior of the front wall. Okay, and it will cause an increasing effect of the pressure on the front wall. Okay, so since this is a closed surface, there will be reflection and that will increase the intensity of the pressure on the front wall. Okay, so the interior front wall will opening. Okay, so what is the load analysis approach? So we assume all openings are combined into a single central opening with an equivalent area of A naught. Okay, so whatever is the opening, okay, due to doors, windows and any other things, we combine them with a single opening area, single area with area A naught. Okay, the idealized pressure time history. Okay, the actual pressure time history will be like this, but what we will do is that we will again try to idealize it. Okay, so the loading will become at time t1. Okay, there will be a time t1 where the loading will become. Okay, and this is the time taken for the shock front to enter via opening A naught. Okay, so this is the time taken to the shock front to travel through this opening inside the structure. Okay, remember what we are trying to calculate. We are trying to calculate the pressure, okay, the internal pressure on the front wall, meaning we are trying to calculate the internal pressure on the front wall. Okay, not the external pressure on the front wall, but the internal pressure. Okay, so the time will only begin when the shock front has entered through this opening. So the pressure will build linearly from T1 to the maximum pressure P max at T2. Okay, so it will attain a maximum at time T2. Okay, and it will be varying linearly. Okay, so this is T and P. Okay. After that, it will decay linearly to T3. Okay, so the pressure time curve will be triangular like this. Okay, so the length of wall loaded by the reflective wave relates to the blast wavelength. Okay, so how much is the length? Okay, how much is the length that sees the effect of the blast load? Okay, so it depends on the blast wavelength. Okay, the maximum interior pressure is a function of incident pressure PSO. Okay, so the maximum interior pressure, okay, this guy, okay, maximum interior pressure, it becomes a function of the incident pressure, it becomes a function of the wavelength, it becomes a function of the blast wavelength. So Pi is a function of incident pressure, blast wavelength and geometry. okay, width to height ratio. Okay. Okay. So, the nature will be triangular in loading and it will be a function of the incident pressure, it will be a function of the blast wavelength and the width to height ratio, okay, the peak pressure on the interior wall. Okay. So, here we can see the variation of the P max based on all these criteria. Okay. Okay. So, this is P max, this is expressed in terms of the width ratio. So, we are shown the maximum average pressure on the interior face of the front wall, and again this is we are getting from the UFC 340, okay, and this curve is the external incident pressure at front face of the building. Okay. So, here basically we are representing the PSO and we are the P max is expressed in terms of PSO and different area openings are considered. Okay. So, A naught is the area opening that we are considering. Okay. So, half, 1/4, 1/8. Okay. So, similarly we can have different plots for different W to H ratio. Okay. So, this depends upon the W to H ratio. So, depending upon the different W to H ratio, we can have different plots. Okay. Window or door breakage is required finite time before pressure relief occurs. Okay. As we have already seen, the breaking of the or the failure of the window or door mechanisms require finite time. Okay. So, this breaking time must be accounted. Okay. This should be taken into consideration for determining the window contribution to the blast pressure on the wall. Okay. Basically, the calculation of this opening area. Okay. So, it should be based upon this breaking mechanism. Okay. If it is able to take it instantly, then it should be included, otherwise it can be excluded. Okay. If covers are resistance and do not break quickly, treat clearing time as that of a solid wall. Okay. There should be no reduction in the clearing time. Okay. If the doors and windows are not able to break instantly, okay, then it has to be considered, the time of the clearing has to be taken as that of the solid wall itself. Okay. So, the blast pressure propagation, interior side wall and roof. Okay. Before this we saw the variation of the pressure on the, here we saw the variation of the P max on the interior wall. Okay. We saw that there will be a time T1 where the shock front is entering the structure, it will rise to a time T2 with a value of P max linearly, and then it will go down to a value of T3, okay, linearly also. And this P max, okay, the maximum internal pressure will be a function of the incident pressure, and it will be a function of the opening in the area, and it will be a function of width to height ratio. Okay. So, similarly, so in the internal front wall loading, we saw that the maximum pressure P max is a function of the incident pressure PSO, it is a function of the opening in the area, and it is a function of the width to height ratio. Okay. And using different graphs, okay, using different graphs from UFC 340 or TM 51300, we can calculate the value of P max. Okay. And the variation of the P max is, first the time T1 will come where the incident shock has entered the opening. Okay. Then it will rise linearly to a time T2. Okay. A time T2 will be there where the maximum value P max will be attained, and after that there will be a decrease in the time, and it will go to a value of 0 at time T3. Okay. So, this is how the internal pressure will behave on the front wall. Okay. After that, we are looking into the variation of the pressure on the interior side of the side wall and roof. Okay. So, the blast pressure will enter the building interior through front wall openings, okay, and which we are treating as a combined opening. Okay. The incident shock will first travel along the front wall, it will affect the shock wave will first affect the front wall, then it will arrive at the side wall where it will be amplified by the reflections. Okay. then will travel across the side wall to the back wall. Okay, finally it will reach the back wall. Again reflections will occur and it will move back across the side wall to the front wall. Okay. So basically there will be a back and forth reflections of the pressure. Okay. And due to this reflection, the effect of the interior pressure will be amplified. Okay. The loaded length of the side wall during this process relates to the shock wavelength. Okay. Depending upon the shock wavelength, the amount of pressure that is affecting the side walls will be depending upon the shock wavelength. Okay. So, pressure time history. Okay. So, the curve applied to both side walls and roof. Okay. So, we saw the pressure time history for the front wall, which is looking something like this: T1, T2, T3, P max. So, this is for the front wall. Now, we will be looking into the side walls and the roof. Okay. And we are making the approximations that this effect on the side walls and the roof is similar. Okay. And for roof, what we will do is that we will swap the structure width to height for calculation. Okay. The only thing we need to do is that swap the width to height ratio. So, first of all, time at which the shock arrives at the front wall is set to T naught. T naught equals to 0. Okay. So, here the time of arrival at the front wall is set to T naught equals to 0. So, it is taken as 0. Okay. So, T1 is the time for the wave to cross the front wall and reach the side walls or roof. Okay. So, T1 is the time where it reaches the side walls or the roof. Okay. So, the linear pressure increase. So, it begins at T1, builds to P max at T2. Okay. So, it will be again it will be building at T2. Okay. So, P max is attained out here. Okay. Then it will hold for some time. Okay. So, from T2 to T3 there will be a constant pressure. Okay. And again it will drop down to T4. Okay. So, there will be a linear decay. Okay. So, the first variation on the interior front wall was like this, the variation on the side walls and on the roof is like this. Okay. So, similarly, as we have used the graph from UFC 3340, similarly we can use the other graphs and calculate the value of P max from there. Okay. So, the maximum pressure calculations. Okay. So, we will see a maximum pressure calculations on the interior side walls and the roof walls. P max is the maximum average interior pressure on side walls on the roof. Okay. Again it is a function of the incident pressure, it is a function of the wavelength and it is a function of the structural geometry. Okay. And for a case where width to height ratio lies between 6 to 1.5, P max is expressed by this equations. Okay. So, either we can use this equations or we can directly calculate from the 340. Okay. So, all these things are being calibrated and already given in UFC 340. Okay. So, for different width to h ratio, the only thing is going to change is the equation for k. Okay. For this range the value of k is this, for this range the value of k is something else, and depending upon other width to height ratio the value of k is being adjusted. Okay. So, we will look into one example. So, what we are required to do is that we are required to find the average peak reflected pressure and the average scale reflected impulse, okay, on the side wall of a 3-wall fully vented cubicle, okay, for a charge of 205 pounds. Okay. So, the data we have been given is height of the structure is 16 feet. So, this guy is 16 feet height of the structure, this guy is 16 feet. Okay. Length is 32 feet. Okay. The length of the cubicle is 32 feet. Okay. The h, okay, the location of the wall height at opening, okay, is 6 feet. Okay. Then wall length at opening, okay, is 12 feet. Okay. RA, the scale distance is directly given. Okay. The charge is 205 pounds. Okay. And n equals to 2. Okay. It is a side wall of 3-wall cubicle. Okay. So, first of all what we will do is that we will characterize the blast loading. Okay. Since nothing is specified, we will calculate the equivalent TNT. Okay. So, you will multiply it by 20%, you will increase it by 20% to get the equivalent TNT. Okay. So, we start from the equivalent TNT. Okay. Then we calculate the ratios and the scale distance. Okay. So, we need H to H ratio, okay, L to L ratios, okay, length to the scale distance ratio and length to height ratios. Okay. So, all these parameters, okay, all the scaling parameters and the ratios we calculate. Okay. After that we calculate the scale distance z, okay, and using the value of z, okay, and all the other parameters we calculate the value of the pressure and the impulse. Okay. So, what we can do is that we can use directly the equations given, or we can directly use the figures also, okay, for given ratios. Okay. So, for given scaled ratios we can directly calculate the reflected pressure and the reflected impulse from there. So, either we can use the interpolation, okay, and we can calculate the values using the different equations, or we can use the values from the figure, okay, like figure 27a or the relevant figure, whatever has to be implemented. Okay. So, this will directly give us the value of the reflected pressure and the reflected impulse. Okay. After that, what we do is that we calculate the load duration on the wall. Okay. So, the duration formula is given, okay, and all the parameters are there. Okay. Either we can get it directly from the graphs also, okay, or what we can do is that we can multiply it with the scaling parameter, okay, W1 over 3 or cubic root of W, okay, and we can get the load duration directly in the respective units. Okay. Here it is given by millisecond. Okay. So, we can take one more example. Okay. So, in this example we need to find the pressure time loads on the exterior front wall and all the interior surface of a rectangular structure with front wall openings. Okay. So, what we are given, the structure has an opening, okay. We need to calculate the pressure time load on the exterior front wall, that is this side of the front wall, okay, the exterior front wall, and interior surface of a rectangular structure with front wall opening, okay, and the interior surfaces also needs to be calculated. Okay. So, what are the inputs that we need? Okay. We need the TNT equivalent, okay, we need the dimension of the structure, we need the area of the front wall opening, and what is the output? Pressure time histories for external front wall, interior surfaces, front, side and back walls. Okay. So, given all these inputs, we can predict the pressure histories on all the surfaces, exterior front wall and all the interior surfaces. Okay. So, we will start as before, we will take the charge. Okay. First of all, we need to determine the TNT equivalency. Okay. If nothing is specified, we increase it by 20% and we get the equivalent weight. Okay. Okay. Second step is to calculate the free field blast parameters. Okay. So, depending upon what type of blast scenario is given, okay, we will have to categorize this thing in the air burst, surface burst, okay, and then we calculate the leakage pressure. Okay. So, these are the different examples given in UFC 342. Okay. So, depending upon these features, we can calculate the free blast parameters. Okay. First thing is calculate the equivalent TNT. Okay. If the actual charge is TNT, then this is just multiplied by 1. If nothing is specified, then we multiply it by 1.2, that is a 20% increase. Okay. After that, we categorize the blast, okay, as air burst, surface burst, okay, and the leakage pressure. Okay. We have to calculate the leakage pressure also. Okay. So, we categorize the type of the blast that is being occurring. Okay. So, first we categorize the equivalent amount of TNT, then we categorize the air burst, and using appropriate examples or appropriate graphs from UFC 340, we calculate the free air blast parameters. Okay. And then depending upon the geometry, we can also calculate the angle of incidence, okay, and the normal distances. Okay. we calculated the standoff distances depending upon where the blast is located with respect to the structure. Okay. So, we have all the free air blast parameters. Okay. So, using this charts, okay, using the charts depending upon the type of blast, okay, we can calculate PSO, time positive, time negative, okay, then length of the blast wave positive, okay, blast wavelength negative, and other free blast parameters. Okay. So, the free field blast parameters are calculated like this. Okay. After that, we start treating the equivalent pressure on the front wall. Okay. So, we find the peak positive reflected pressure as a function of PSO and alpha. Okay. So, from this graph we can calculate this thing. Okay. Then we find the peak positive reflected scaled units. Okay. We calculate the impulse. Okay. Okay. And since this is divided by cubic root of W, okay, this is a scaled impulse. After that, we multiply it by the cubic root and we get the impulse in the absolute sense. Okay. We find the reflected sound speed as a function of the PSO, okay, the incident pressure. We calculate the reflected pressure clearing time, okay, given all the equations that we have seen, and then we construct the exterior pressure time loading curve. Okay. As we have seen in the previous week, we construct the exterior pressure time loading curve, okay, which used to look something like this. Okay. So, this was the equivalent pressure time curve for exterior loading. Okay. Okay. The only thing that changes here is that we are calculating the clearing time also. Okay. So, the time we are adjusting and we are also calculating the clearing time. Okay. In the last week there was no clearing time. Here only thing is that the time is being adjusted for the exterior surface and the clearing time is being calculated. Okay. And then we construct the exterior pressure time curve and we determine the scale incident wavelength. Okay. And then we multiply it by cubic root of weight to obtain the actual values. Okay. So, categorize the blast charge, categorize the type of burst, calculated the free field parameters, and from the free field parameters we calculated the same equations used for the exterior loading. Okay. And only thing is that we have to adjust for the clearing time because there are openings out here, and then we construct the exterior front wall blast loading, okay, which will look something like this. Okay. T equivalent positive, T equivalent negative. Okay. Okay. After that, we are going to construct the interior front wall blast load. So, as we have already seen in these examples, depending upon the geometry, okay, we can calculate the value of P max, okay, and using the different figures we calculate the rise time and the duration. Okay. We calculate the time T1 to time T2 and then T2 and then T3. Okay. So, we calculate the interior load on the front wall. Okay. So, this is how we construct the interior front wall load. Okay. After that, same using this equations, okay, we calculate the pressure on the side walls and this is P max. Okay. We calculate the pressure on the interior side walls interior. Okay. And after that, using the same equations, we calculate the back wall interior blast loading. Okay. So, using the same procedure and extending it to the interior wall surfaces, we are able to calculate the pressure on the front wall, we are able to calculate the external pressure on the front wall, we are able to calculate the internal pressure on the front wall, internal pressure on the side walls and the back walls. Okay. And final assembly, what we will do is that we will construct the full pressure time load curve on the exterior front wall, interior front wall, side walls, roof, back wall, and then we will use this curve to design for the blast loading. How we will use this thing? Okay, if there is an opening, we have constructed the exterior front wall, we have constructed the interior front wall, we have constructed the exterior side wall, exterior side wall, we have constructed the interior side wall, interior side wall, we have constructed the interior roof, exterior roof, and then we have constructed the exterior back wall and the interior back wall. Okay. So, all these pressure quantities we have. Okay. If there is opening, the interior quantities will be present. If there is no opening, then the interior quantities will not be present. Okay. Once we have all this pressure loading, what we will do is that we will augment the effect of the this things. Okay. So, what we will do is that we will take interior effect of the interior positive, okay, interior positive, okay, that will try to make it outside, and then we will take the effect, okay, of the exterior negative, that one will also try to move it outwards. Okay. So, interior negative effect and interior positive effect and exterior negative effect will take them together, okay, because both are trying to push them outside. And similarly, we will also analyze for exterior positive, which is trying to put it inside, okay, and we will design for the worst case scenario. Okay. Why? Because if it was a static case, then the interior positive and the exterior positive might have cancelled out each other or might have reduced the effect of one another. But here, since the time when the exterior effect is taking and the time in which the interior effect is taking is not the same. Okay. So, in order to account for the worst possible case scenario, we will add the effect of the interior positive with the effect of the exterior negative, and the exterior positive will analyze it separately. Okay. So, this is how we will combine the effect, okay, in order to calculate the total effect of the blast loading on the structure. Okay. So, with this we have covered the effect of the blast loading on rectangular boxes, okay, with or without opening, and we have followed a procedure which has, in the first phase, first of all we need to calculate the equivalent TNT. Okay. Once we calculate the equivalent TNT, we calculate the type of blast. Okay. From the type of blast we calculate Z, and from Z we calculate the free field parameters. Okay. From the free field parameters, using the case, okay, closed case or opening case, okay, we calculate the exterior loading if it is a closed case, exterior on the front wall, exterior on the side walls, exterior on the roof, exterior on the back wall. Okay. And if this is an opening case, we calculate the similarly all the exterior quantities, as well as in addition to that we also calculate the interior quantities. Okay. And after we have all the equivalent pressure quantities, we combine the effect of the interior positive with the exterior negative and get the maximum response quantities, and then we also calculate the response quantities due to the equivalent exterior positive pressure duration, and we design for the worst case possible scenario. Okay. So, this is the procedure that we are following. I hope the explanation is clear. I request you to practice it, okay, and if there are any issues, feel free to contact me. Thank you for your time. Thank you.